These are the contents which we'll be going through in this particular session. So first is the thunderstorm model, along with the sum of theory and some numericals, and later on we'll move on to determine the optimum number of rain gauge stations in a given catchment. And we'll also be seeing some methods to estimate the missing rainfall. And we'll also see some methods to estimate the average rainfall for a catchment. And later on, we'll be seeing how to estimate the rainfall for a particular location where there is no rain gauge. So in that, we'll be looking at the inverse distance weight method, which is a most popular method used for estimating the rainfall at an ungauged location. Okay, echo. Is it fine now? Okay, I think it should be fine now. Okay, we'll move on to the thunderstorm cell model. So the thunderstorm cell is because of the forms due to the effect of convection when there is a hot and humid day where there is when there is much of moisture present in the air. Because of the heat, the less denser air rises up, and then while rising up it condenses and then it forms as a convective precipitation. And this happens in most of the urban areas during summers, and we receive the short and intense rainfalls. So now we are going to determine what is the intensity of this thunderstorm cell, and for that we need to know what are the parameters at two different levels. One is the base level, the ground level, and the other region is the top of the thunderstorm model. So these are the atmospheric parameters. In the last week we have seen different parameters which are the pressure, temperature, specific humidity, density of the air, then velocity of the upward air current. So the basic structure of the thunderstorm model is displayed here. So the thunderstorm model has an inflow region through which the air with the moisture and the vapor flows into the region, and it gets uplifted because of the upward air current, and as it rises up it condenses and it forms the precipitation in that particular area. And then after the precipitation, the rest of the air flows out of this region as a dry air, and again it goes into the kind of a loop, and then it goes on for continuous time. So these are the different regions. And in the convective cell we'll be deriving the expression for the rainfall intensity by using the control volume approach. So this diagram represents the convective cell, and the green line is the control volume. So here we are defining at the near to the surface, from the ground level we will have the cloud base at some particular height, and that is represented, that distance is represented by delta Z1. Then we have the inflow region through which the water vapor goes in, and we have the outflow region through which the water vapor goes out. And at the top we have the region where this vapor comes out, and we have the cloud top. So that region is defined, that depth is defined as a delta Z2, and this control volume is basically a cylindrical in shape, and it has a height of h. This height represents the height from the cloud base to the top of the convective cell. So the moisture enters the inflow region and it rises due to the convective action and it produces the precipitation. Then the cool and dry air flows out of the outflow region and it again enters the cell, and this is the driving force for the continuous precipitation to happen over a particular area. And this outflow region is basically 8 to 16 kilometers above the ground level. So coming to the derivation, so we have to determine the atmospheric parameters at section 1, which is at the ground level, and we have to determine the same at the section 2. So we'll be using the continuity equation which we derived using the Reynolds transport theorem to analyze this thunderstorm model. So the basic notation of the Reynolds transport theorem is given here. So on the left hand side we have the system property which is dB by dt, which is equal to rate of change of the intensive property that happens within the control volume plus the amount of matter which goes in and goes out of the control surface, that is represented by the second term. So if we recall, for moist water vapor we have the continuity equation. So in this, the extensive property is basically the mass, and here the intensive property, which is the beta, is not equal to 0 because we have a phase change from one phase to another. So water vapor basically changes from vapor to liquid and then it changes from liquid to vapor again. So in that case the intensive property will not be equal to 1. So here we are representing it as another parameter, which is the specific humidity. And since there is a change in phase from one phase to another, the term on the left hand side is not equal to 0 and we represent it as the mass flow rate. So then we substitute all these values in the Reynolds transport theorem, which is this equation, and we get the mass flow rate on the left hand side is equal to d by dt of integral over the control volume, specific humidity into density of dry air into volume, plus the integral over the control surface, which is near the inflow region as well as the outflow region, specific humidity, which is the intensive property, then density of air, then we have the velocity vector and area vector. So here we are considering the cross-sectional area of the cell as A and precipitation intensity as I. So the mass flow rate is given by density into volume. Since it is flow rate, we are dividing it by time, so which will have a unit of kg per second. So substituting these expressions, we get the mass flow rate as density of water into area of the cross section multiplied by the precipitation intensity. And in the first week, there was a lecture in which this sign convention would have been introduced. So here, as condensation happens, we are removing the moisture from the air. So it is a negative. In case if it is evaporation, we are supplying moisture to the air. So in that case, it will be positive. So the mass flow rate has a negative sign. And we are going to consider a very small time interval, and during that small time interval we are going to assume a steady state condition. So the term on the first term on the right hand side, which has a time associated with it, can be neglected since it is steady state. So the rest of the expression will be mass flow rate is equal to the integral over the control surface and the remaining expression. So this integral over the control surface is outflow minus inflow. So we are just substituting the parameters in terms of outflow and inflow. For the inflow region, we have given the notation of 1, and for the outflow region we have given the notation as 2, and rearranging this equation, we are getting the mass flow rate on the left hand side is equal to inflow region minus the outflow region. So now coming to the inflow region, so we have seen that this is the ground level and this is the cloud base. So now we need to determine what is the specific humidity, what is the density of the air, and what is the velocity and what is the area. So we are going to derive based on this. So here we need to consider the delta Z to be as small as possible because the atmospheric parameters changes with respect to the elevation. So when this is considered as small as possible, we can make an approximation and calculate the parameters. So here, so this control volume is a cylindrical volume, and the area through which the vapor enters is given by this control surface, and this is a cylinder and it has a surface area of pi d into h. Here h is the delta Z. So now considering this as the equation 1, we'll move on to the outflow region. So in the outflow region, we have the dry air carrying the vapor, dry and cool air that is coming out of the cell. So, but we don't know how to estimate the specific humidity or density of the air, and here we do not know how to estimate the specific humidity, density of air and velocity at the region 2 because we don't have the dry air parameters. So we are going to convert this parameters into the known parameter, which is the parameters at the ground level. So here for dry air, we know that here there is no phase change that is happening. So there is no change of phase from vapor to liquid or liquid to vapor. So in such cases, the intensive property is basically the mass itself and it is equal to 1. So when the intensive property is equal to the mass, and it does not change with time because of the conservation of mass, the left hand term will become 0. And we are also assuming a steady state condition, and the first term in the Reynolds transport theorem is associated with time, and that term also can be neglected. So the remaining term is, so your left hand side will be 0 and the remaining term will be only the integral over the control surface. Here since we are dealing with only the dry air, so we need to give the appropriate density. So here we are giving the density of dry air, and we have the velocity vector and the area vector. So we have seen the expression already. Density of air can be written as density of the vapor plus density of dry air. So from this we are rearranging to get the density of dry air. So density of dry air is equal to density of air minus density of the vapor. And from the definition of specific humidity, we also know that it is defined as the ratio of density of the vapor to the density of the air. So from this we can simplify the expression and write it as rho v is equal to specific humidity multiplied by dry air. So substituting these two equations in the, we will get the density of dry air in terms of density of moist air itself, which rho d is equal to rho a into 1 minus qv. So this is a simplified expression. Now we are at the outflow region. So similar to the inflow region, the outflow region is also a cylindrical in shape, and we have the control volume something like this, and the dry air comes out of this particular surface. So we need to determine, so we have this equation. This is basically, this can be written as outflow minus inflow. So that is what I have written here. So this is outflow minus this is inflow. So substituting the expression for rho d which we found earlier, so dry density we have written it as 1 minus qv into rho a, and here we are giving the upward air velocity as v itself, and this cross section area a is the height of the lateral surface area of the cylinder, which is given by pi d into h. Your h here is delta z2 minus what is happening at the level 1, and we are equating it to 0. So from this we can get the expression for the parameters at the outflow region in terms of as a function of the parameters at the inflow region. So we have got this equation 2. Now coming back to the continuity equation which we have written for the moist air. So we have stopped at this place. So we have basically determined this parameter. So we are going to substitute the equation 2 in the equation 1, and we are going to simplify it. So upon simplification, we are getting so here we are just taking LCM and then we are simplifying it, and if we simplify we will arrive at this particular expression. So here we have another area. So this area represents the cross-sectional area through which the moist air is entering the system. So that is, if we have a cloud base like this, our air is entering through this particular cross-sectional area, and this can be written as, this cross-sectional area is area of the cylinder, and this is pi d square by 4, where d is the diameter of cloud base. And substituting, and we are deriving the expression for the intensity of the rainfall that happens because of the convective precipitation. So now we can go, we can solve the problem for this thunderstorm model. So the question is, a thunderstorm model is 5 km in diameter. This represents the cloud base, and the height, and this cloud base is at 3.5 km from the ground level. So we have the delta Z1. So this is the delta Z1 and this is the diameter, and the surface conditions nearby indicate the saturated air conditions with air temperature. So they have given the temperature at the ground level and the pressure also at the ground level. So they have given the pressure, and this is the wind speed, that is the upward air current that is happening, and they have given the lapse rate as 7.5 degrees per kilometer. So we can calculate the temperature at different levels and an average outflow elevation at 10 km. So this is the total height of the thunderstorm model. So representing all the parameters as a diagram. So we are having the diameter, we are having the total height, and we are having delta Z1. Now the given parameters are so this is the near surface condition at the ground level. So we have been given velocity as 2 meters per second, and the density of the water is 1000 kg per meter cube. This is a known quantity, and we have delta Z1 as 3500 meters, and we have the diameter of the cloud base as 5000 meters, and we have been supplied with the lapse rate, which is given as 7.5 degrees per kilometer. So now we are going to divide the entire cell into 3 parts. So this is the first zone, this is the second zone, and this is the third zone, and we need to determine the parameters: pressure, saturation vapor pressure, specific humidity, density of dry air. Then we need to estimate the temperature. Then these are the parameters which are required. So we are going to estimate all these parameters. So for that I am going to draw a table. So this is the elevation at which we are going to take. Then we have temperature in degree centigrade, and temperature we require in Kelvin also. Pressure in terms of kilopascals. Density of air in terms of kg per meter cube. Saturation vapor pressure in terms of kilopascals, and we have to determine the specific humidity. And its unit is kg of water per kg of moist air. So we are going to determine the parameters at 3 different elevations, that is at the ground level, at the cloud base, and at the top of the thunderstorm model. So first we need to calculate the temperature. So at ground level, temperature is given as 35 degrees centigrade. So we need to calculate at 3.5 kilometers. So that is temperature is 35 minus, using the lapse rate, 7.5 into 3.5. We have 8.75 degrees centigrade at the cloud base, and at the top of the thunderstorm model, so we have minus 40 degrees centigrade. And then we need to estimate the temperature in Kelvin as well. So that is temperature in degree centigrade plus 273. So at the ground level, the pressure is given as 100 kilopascals, and we need to estimate the pressure at different levels. So for different elevation, we have the expression Pressure at any level, any second level, is equal to pressure at the first level multiplied by temperature at the second level by temperature at the first level raised to the power G divided by Ra into T. Sorry, it is Ra into alpha. So here temperature is in Kelvin and alpha is in degree centigrade per meters, and it's not in kilometers. So we are going to estimate the pressure at 3.5 kilometers. So that is P2 is equal to pressure at the ground level is 100 into temperature at the second level is 281.75 divided by 308 Kelvin. G is 9.81. Ra is the gas constant for dry air, and it has a value of 287 joule per kg Kelvin. Into this is 7.5 divided by 1000. I am converting it into meters. So pressure at the second level will be equal to 66.633 kilopascals. So similarly at 10 kilometers, (28.032 kilopascals). So now we have determined the pressure. Next is we need to determine the density of dry air. So to determine the density of dry air, we have the expression pressure divided by Ra into T. So at 0 kilometer, which is the ground elevation, we have pressure 100 kilopascals into temperature in Kelvin is 308. So this will be equal to 1.131 kg per meter cube. Then similarly at 3.5 kilometers, then again at 10 kilometers, so we have calculated the density of dry air. So next we need to determine the vapor pressure at each of these levels. And we know this expression already from the previous lectures. Here temperature is in degree centigrade, and you will get E in terms of kilopascals because I have used 0.611 here. And at 3.5 kilometers. So we have calculated the saturation vapor pressures at different levels. So next we need to determine the specific humidity. That is the last parameter. So we know the specific humidity's equation 0.622 into saturation vapor pressure by the total pressure. Then at 3.5 kilometers, we have specific humidity at kg per kg. So we have estimated the specific humidity at different levels. Next, between the cloud base and your ground level, your atmospheric variables are going to change. So we are going to compute the average of the density of dry air at that place. So rho A1 is the density of the air at the ground level plus density of air at 3.5 kilometers So this value will be equal to kg per meter cube. So next is the average specific humidity. So this is QV1 plus QV2 by 2. Now we have all the parameters to compute the intensity of the precipitation from this thunderstorm cell. So the intensity is given as 4 times the density of average density of air into V1 into delta Z1 divided by rho W into D QV1 minus 1 bar minus QV2 divided by 1 minus QV2. So this is the expression, and we can compute. It's just direct substitution. So the intensity of the precipitation is 1.2246 into 10 to the power minus 4 meter per second, but we represent the intensity of the rainfall in terms of millimeters or centimeters per hour. So if we convert it, so I'm converting it to centimeters per hour. It is around 44.084 centimeters per hour. So this will be the intensity of the precipitation that happens because of this convective cell. So now we have completed the thunderstorm cell model. Next we can determine the next topic is optimum number of rain gauges, and followed by the different ways in which you can analyze the precipitation data. So why do we need optimum number of rain gauges? So rainfall has a very high spatial and temporal variation. So to capture this spatial and temporal variation, we need a network of rain gauges, so that we can analyze many of the models like HMS or other hydrologic models, and we can derive some interesting conclusions, and we can use it for flood forecasting or any other applications. So now we need to estimate what is the optimum number of rain gauges in a catchment. So for that, I have just listed out the steps how to solve the problem. So you will be given with either tabular data, or you'll be directly given the mean and the standard deviation which we need to compute. So if they are given in the tabular format of rain gauge data, we need to first estimate what is the mean of the data and the standard deviation of the data. So this standard deviation is a sample standard deviation. So we have two standard deviations. One is sample standard deviation and another one is the population standard deviation. So here we are using the sample standard deviation, and after estimating the mean and the standard deviation, we need to determine the coefficient of variation, which is simply the ratio of standard deviation to your mean. This we need to determine in terms of percentage, and you will be given with the error percentage in your question. So this error percentage represents the maximum acceptable limit of error that is allowed while estimating a average rainfall for a given catchment. So your coefficient of variation divided by the acceptable limit of error will give you the, and the square of it will give you the total number of rain gauges. So here we will get the total number of rain gauges, but in some questions you will be asked to find out what is the number of additional rain gauges. So number of additional rain gauges is equal to the total number of rain gauges minus the number of rain gauges that is already existing. So here this is the additional rain gauges, and this is the total number of rain gauges, which is the N optimal, minus the number of rain gauges that is already existing, that will be given in your question. And in some places you will be asked to find out what is the number of recording type of rain gauges is required. So we have different types of rain gauges: self-recording, recording type, non-recording type. So in some places you will be asked to determine what is the number of recording type of rain gauges needed. So generally we need to have at least 10% of the total rain gauges. This is 10% of total, which means this is N optimal. So 10% of the N optimal should be of recording type, and we need to remember that we need to round off N optimal always to higher value. So now we can solve a question in this. So the Adayar basin has 3 non-recording rain gauges. The amount of rainfall recorded for each of the 3 stations are given. So we have 3 rain gauge stations in the Adayar basin, and the annual rainfall of that particular station is given. Now we need to determine what is the number of optimal rain gauges if the error is 8% for computing the average rainfall, and we need to determine what is the number of additional rain gauge that is required, and we also need to determine what is the number of recording rain gauges and the non-recording rain gauge that is required. So for that, first we need to estimate the mean. So we are estimating the arithmetic mean. So here mean is equal to 101.33 centimeters. And next we need to estimate the sample standard deviation. So your sample standard deviation will have a n minus 1. So and this value is found to be 18.037 centimeters. Sorry. Now we have the mean and the standard deviation. Next we can determine what is the coefficient of variation, which is simply the ratio of standard deviation to your mean. And we need to estimate this in terms of percentage into 100%. So now we are getting 17.799%. Now you have n optimal is equal to coefficient of variation divided by error percentage the whole square. Your error percentage is 8 and roughly you will get 4.95 stations. So we can round it off to 5 stations. So this is your answer for the first part. Then for the second part, you have been asked to find out what is the additional number of stations. N additional is equal to N optimal minus number of stations that already exist. So you have 2%, two stations. So this is the additional number of stations required. Now we need to find out N recording, number of recording rain gauges. That is 10% of N optimal, which is 0.5. So let me write like this. So this we can round it off to 1. So your split up will be number of recording stations needed is 1. Number of additional stations are 2. N existing equal to 3 stations. N total is equal to 5 stations. So moving to the next part, sometimes the rain gauges will not be operative during some of the rainfall events. It may become inoperative or it may be damaged, and in that cases we need to estimate the what is the rainfall that happened in that particular station. So for estimation of missing data, we have two different methods. One is the arithmetic method and another one is the normal ratio method. So when to use which method? So there is a check which we need to make while solving this kind of a problem. So the check, I have explained how to check it here. So we need to use normal ratio method when the normal rainfall of all the other stations that was operative differs by more than 10%. So this is the statement. So if it is not following this, then we can use the arithmetic ratio method. So to explain this, let's say we have 4 stations A, B, C and D, and these 4 stations are having normal annual rainfall N1, N2, N3 and N4. Now these 4 stations in a year record the precipitation as a P1, P2, P3 and P4. So because of some operational issues, one of the station B was not recording the rainfall. So we don't know what is the precipitation 2. Now we need to find out this precipitation 2. So how will we check? First, station B was found to be inoperative. So we need to take the plus or minus 10% of the normal rainfall of the station 2. So we need to you would be given in the question normal rainfall for the station which was inoperative. So we need to compute what is the 1.1 times. So 10% increase and 10% decrease, that is 1.1 times of N2 and 0.9 times of N2, and we have a range alpha comma beta. So if all the other stations that is A, C and D, though their normal rainfalls are within the range of alpha and beta, then we can use the arithmetic mean method. Even if any one of the normal rainfall deviates above this range or below this range, then in that case we need to use the normal ratio method. So now next, coming to what is arithmetic mean method, is simply the average of the stations. And for the normal ratio method, we have the formula. So precipitation of the station for which we need to find is on the left hand side, is equal to normal rainfall of that particular station divided by n minus 1 stations. So we are considering the other 3 stations only, multiplied by summation of precipitation for the particular station which was operative divided by the normal rainfall of the station which was operative. So here I have given the explanation for each of the terms in the formula. Now we can go for a problem. So the normal rainfall at the stations A, B, C are given as 170.6, 180.3 and 165.3 centimeters. In 1987, the station B was found to be inoperative, and the stations A and C recorded 153 centimeter and 145 centimeter respectively. Estimate the average rainfall of the station B in that year. So now we need to check. So the station which was inoperative is station B. So the inoperative station is B, and it has a normal rainfall of 180.3 centimeters. Now we have to compute 1.1 times of NB, which is 198.33 centimeters, and we need to compute 0.9 times of NB, that is 162.27 centimeters. So we have our alpha, we have our beta, and we have the range alpha comma beta, 162.27 and 198.33. So from the question we can see that the normal rainfall of all the other 2 stations are within this range. So here NA and NC are within the range alpha and beta. So we can use normal arithmetic mean method. So we have the precipitation in the missing station is equal to So next, one more example for the normal ratio method. So in a watershed, 4 rain gauge stations are given, P, Q, R and S, and the depth of the normal rainfall in the station is given as 70, 75, 80 and 105 centimeter respectively. The rain gauge station at the station R became inoperative that year, and the other three stations recorded the rainfall as 90, 65 and 75 centimeters. Now we need to estimate the average rainfall of that station in that year. So again, here the station R was inoperative. So we need to normal rainfall of the station R is 80 centimeters. So alpha is equal to 1.1. So we need to compute 0.9 times of, which is 80, which is 72 centimeters, and beta is, which is 88 centimeters. Here, normal rainfall of the station P and normal rainfall of the station S are outside the range alpha and beta. So use normal ratio method. So PR is equal to NR by, there are 4 stations, we are using N minus 1, precipitation at P divided by normal rainfall at P, PQ divided by NQ, PS divided by NS. So here we have 80 by 3 into 70 by 90 plus 75 by 65 plus 105 by 75. So we have the precipitation at the R station as 88.84 centimeters. So now we have seen up to estimation of missing rainfall data. Next is determination of average rainfall. So to determine the average rainfall, we have Thiessen polygon method, we have the isohydral method. So I'm going to display some of the maps in which you can see how the Thiessen polygon and the isohydral maps are drawn for a watershed. So this is a watershed boundary. This is in Tamil Nadu near Chennai. So the name of the watershed is Adayar Basin, and we have the different rain gauge stations which are shown as red dots in this map. So for this network, we are going to see how the Thiessen polygon looks like. So here you can see for each of the station cutting across the different subbasins, we have the influence area from each of the rain gauge stations. So this is how a Thiessen polygon looks like for a watershed. So in the problem, you will be solving any one of the subbasins. So it won't be an entire watershed, it's just one of the smaller subbasins. And this is a isohydral map. This is for the entire Chennai basin for the rainfall which happened between 17 to 19 November 2021. Here you can see the ISO heights which are shown in terms of blue lines along with their rainfall values. So if I zoom it in, you can see the ISO heights. So the red dots are the stations, rain gauge stations, and you can see the ISO heights in the blue line with the value marked on it. So this is how a isohydral map looks like for an entire watershed. Okay, so we'll move on to solving some problems related to the Thiessen polygon method and the isohydral method. So first is the Thiessen polygon method. So for a given catchment, we need to take only the rain gauges that are within the catchment. So we should not consider the stations which are outside the catchment. These stations might not have a contributing area within this particular watershed. So this is something which you need to remember. So here I have shown a catchment. So this is, let's say, one of the subbasins, and it has 5 stations which I have displayed: S1, S2, S3, S4 and S5. So we need to draw a Thiessen polygon for this series of rain gauges. So we have some rules to draw this Thiessen polygon. So we need to join the rain gauges by a series of triangles, and these triangles must not overlap with each other. And after drawing the triangles, we need to draw perpendicular bisector to each side of the triangle and intersect that perpendicular bisector to the catchment boundary. So I'll draw the Thiessen polygon once again. So here I have joined the different stations with the pink color dotted lines. Now I'm going to draw the Thiessen polygon. So for this particular side, the perpendicular bisector will look something like this. Then for this side, it will look something like this. And we need to stop at the place where these two perpendicular bisectors meet. So for this particular side, I'm going to draw a perpendicular bisector like this. Then continuing, so this is your Thiessen polygon, and A1, A2, A3, A4 are the influence areas. So here I have not considered S5 because it is outside the watershed. And to estimate the average rainfall, it is simply P bar is equal to product of your station rainfall multiplied by the influence area for all the stations divided by the total area. So now we can solve a question related to the Thiessen polygon. So here question is, assume that a catchment is a square shape. So in reality it will not be square shape, so we are just assuming with side A there are 5 rain gauges P1 to P5 in the catchment. So each corner of the square represents one rain gauge, and the fifth station is at the centroid of the square. So let us first draw how the catchment looks like. So the catchment is a square and it has a rain gauge at 4 corners. And another rain gauge is at the centroid. So centroid is at the place where the two diagonals intersect. Okay, now we need to join all these stations by the series of triangles. So I am joining each side with a triangle, and these triangles should not overlap. So now I have drawn the triangle. Now I need to draw the perpendicular bisector for each side of the triangle. So, and intersect with the catchment boundary. So for this side, I will draw a perpendicular bisector like this. Similarly, for this side, okay, let me just so the side of the square is A, and this will intersect exactly at the midpoint of the side, so that is A by 2. So you will have the different contributing areas, so I am just shading it, so that is and your final area is inside the let's mark the areas. So this is A1, A2, A3, A4, A5. Okay, moving on to the question. So we have drawn the Thiessen polygon for this particular catchment. So the area of the influence we have marked. So now the first part is construction of the Thiessen polygon, which we did just now. Now we need to find out what is the contributing area of each of the station. So your contributing area will be in terms of, so your A1 will be equal to, A2 will be equal to, A3 is equal to A4, which is the area of that small triangle. So that is half into base is this much, and your height is also A by 2. Which is simply A square by 8. And the area of the inner rectangle, inner square, that is A5. Area of the inner square is a square by 2 because this side is equal to a by root 2. So now we can compute the, so we have computed the contributing area. So next part of the question is, if the side of the square is 30 km and the precipitation recorded at the stations are 300, 285 and 272, 290 and 288, then find the average precipitation of the watershed. So here we have P1, P2, P3, P4 and inside we have P5. So we can compute average precipitation is equal to P1A1 plus P2A2 plus P3A3 plus P4A4 plus P5A5 whole divided by summation of all the areas. So P bar is equal to, so here A1, A2, A3 and A4 are equal, so I am just going to add the precipitation values for that. Into the area is A square by 8, so that is 30 square by 8 plus P5 is 288 into A square by 2. Whole divided by your summation of the area, which is 271.375 mm. So next is the isoheightal method. So the isoheights are nothing but line connecting the points of equal rainfall, and the isoheights is not same, unlike Thiessen polygon. If the stations are the same for over a long period of time, your Thiessen polygon is not going to change for a given watershed. But in isoheightal method, each event will have a different kind of a pattern, and you will have a different isoheight. So here you can see there is a small circle which is the P6. So when you have some question which has this kind of circular areas, how to compute your average precipitation, what is the influence area that you will take, and what is the precipitation value which you will take. So if you see for this kind of catchment with a particular isoheight for an event, so we can write the average precipitation as P bar is equal to P0 plus P1 by 2, average of the two isoheight into the enclosing area that is within the catchment. So but for circular isoheights, closed isoheights, you need to take the precipitation which is given outside this region itself. We should not take the average value of the precipitation. That is the only change which we have to make, and we can compute the average rainfall. So moving on to the question, here you have the isoheightal contours for a 24-hour storm over a catchment, which is represented here. So you have 6 different isoheights, and the catchment area is given. The area is also given in the form of a table. So this will be your area 1, area 2, area 3, area 4 and area 5, and these are the precipitation values for that particular isoheight. So we have a contour pair and the area is given in the kilometer square. It is just a direct substitution. So P bar is equal to P1 plus P2 by 2 into A1, P2 plus P3 by 2 into A2, P3 plus P4 by 2 to A3, so P bar is equal to whole divided by so this is your average rainfall. So the last topic for today's session is the estimation of the rainfall at the ungauged station. So here we are going to use the method called as reciprocal distance square method or inverse distance weighted method power 2. So here you have a catchment and you have some rain gauge stations, but you need to if you want to estimate the rainfall at any other point where the station is not located, we can use this concept called as inverse distance weighted method to determine the rainfall at any particular point. So for that we need what is the precipitation values at the stations and what is the distance of the station from the point of interest. So P is the point of interest. So what is the distance of the different stations from this particular point? And if we know these three things, we can calculate the what is the precipitation at the point of interest. So precipitation at the point of interest is directly proportional to W. W is the weight. So here the weight is given as here if you see the method name, it is reciprocal distance or inverse distance. So 1 by D is the inverse of your distance and we are using a power 2. Then you can compute the precipitation at the point of interest as P is equal to summation of I is equal to 1 to M, that is the number of stations, Pi into Wi divided by summation of Wi. So here we can solve one small problem. So a catchment has 3 rain gauge stations S1, S2 and S3 as shown in the figure, and it recorded rainfall for a particular event as 2 cm, 6 cm and 5 cm. Now we need to estimate the rainfall at an ungauged location P on the catchment using the reciprocal distance weight method. So let's see how we can proceed with this. So first the distance is given, the precipitation values are also given. So we can just directly apply the formula. So P is equal to P1 into 1 by D1 square plus P2 into 1 by D2 square plus P3 into 1 by D3 square whole divided by the summation of your weights, that is 1 by D1 square plus 1 by D2 square plus 1 by D3 square. So if we apply, so precipitation at station 1 is given as 2 centimeters, So here it is 2 centimeter, this is 6 centimeter, and this is 5 centimeters. So 2 centimeter into 1 by distance square. So station 1 is 3 kilometers, so 1 by 3 square, plus precipitation 2 is 6 centimeters into 1 by 2 square. The station 3 is 5 centimeters into distance is 1 by 4 square, divided by the summation of your weights. So your precipitation at the point of interest is 4.819 centimeters. So in this way you can estimate the precipitation at a point of interest using the inverse distance weight method. So for a real life example, if you see, for the same Adyar catchment, so if our point of interest is the pink color dot, we will define a radius of influence. So it will take the points only within the radius of influence, and you can determine the distance from the point of interest to the stations, and then you can determine what is the precipitation at any of the point in the catchment. This has been computed using the inverse distance weight tool in QGIS. It's a GIS software. So I have solved some of the problems related to this week's content, and I have also solved a example problem on the reciprocal distance method which was taught. Hello Dinesh. Do you have any particular doubt related to this week's content? Hello. So if you have any doubts, you can ask now. Do you have some doubt? Hello. Okay, if you don't have any doubt, then I'm closing today's session. In this session, we have seen the following contents. So we have solved a thunderstorm cell model numerical, then how to determine the optimum number of rain gauge stations, then how to estimate the missing rainfall data using arithmetic mean method or the normal ratio method. Then we have seen how to draw a Thiessen polygon, then how to find the average precipitation using the isohydral method, and a small example for the inverse distance weight method. So this video and the notes and everything will be uploaded to a common drive folder, and it will be shared by the coordinators. Thank you.